This is another video about generative adversarial networks. This one is a work published in Computers and Geotechnics in 2024. In this case, I'm not the sole author. I'm with my colleagues Xiaofai Zhao and Hanzi Li from the same institution, Zhejiang University, and Liang Lei from Westlake University, also in Hangzhou, China. Okay, so what are the main novelties of this work? So one is that it's 3D. We already saw this in the previous work, but we'll see that here we expand the capability of the model with the larger images. And we're also dealing with a more complex material that has more phases than before we had in this publication, we only had one phase, so this was a solid with a given porosity. In this case, we have a partially frozen salty sand. So this means we have the solid and the pores are partially filled with water, which is partially frozen. So these are four phases, which is more complex. So what's the target of this work? The target is to use a generative adversarial network to learn the underlying features of an image that comes from an X-ray CT of a partially saturated sand, and to be able to synthesize images with the highest up-to-date size for this application, which is 80 voxels, which by the way it's the size we need to be able to apply homogenization techniques and to consider that we have an REV size. So REV stands for representative elementary volume. You see that for sizes below that, the averaging of the gray level is not constant, but more or less after 80 it's pretty much constant. So that's why this allows us to say this is an REV. Okay, so we needed this size, so we did all was needed to update the GAN model to be able to synthesize this size. If you make the math, 80 cube in 3D, it's 512,000 voxels, so that's like half megavoxel, which is quite significant. It requires a lot of computing power. In particular, it requires a lot of dedicated GPU memory. If I remember well, it required more than 12 gigabytes. So you can do this with any GPU available in your laptop. You need a bit more powerful rig. Okay, unless of course you have a very powerful gaming laptop or something like that. Okay, this is the diagram of the generative adversarial network we are using. It has nothing particularly different than the diagrams we saw before. The difference here is that we updated the network so they are able to reproduce 80 cube voxel images. So this needs some tweaking of the size of the kernels and so on, so it uses a bit less memory, and also increasing the depth of the networks by one layer, more or less, for the generator and discriminator. Okay, so we have a database of 744 images that have been obtained by bootstrapping single image of a sample taken by X-ray CT. So what we want is to produce synthetic images, so fake samples, that not only look like the real one, but also have some of the properties of interest, like physical properties, also matching the real images. Okay, so as I said, this size, 80 cube voxels, is the highest up-to-date applied in this kind of material. So you remember in the previous publications, I introduced some physics supervision in parallel to the network. Here, the challenge of the generative adversarial network by itself is already big, so we decided to go with just the generative adversarial network, produce good enough images, and then measure the posterior metrics and provide this so in the next research we can add the parallel the parallel physics supervision. Why we do this? Because if we start adding supervision here with a network that is growing and growing in size, we can end up with suboptimal solutions in the future, and we will keep using them. For instance, the hyperparameters of this network, such as the dimension of latent space and the batch size that we use to fit the discriminator, that is very important for the result. But if we do not spend time to validate that, we'll just keep using the values that work for the smaller images, and at some point we will get a bottleneck because of this. So that's why we decided in this work to make a study of what's the optimal latent space and batch size. So those are these dimensions here, latent dimension, which is the dimension of this latent space, is a space from which you draw random vectors or vectors of random values that fit the generator, and it's a space in which the features of the features that learns the generator from the database are code. Okay, and then the batch size, in which here we use 112, which are values that we use in the past for smaller images, and those work well. So now the aim of this research is to find the optimal these two values for this particular application. So how will we decide what's optimal? We'll measure a posteriori metrics of these images, and the posteriori metrics will be some significant measurements for this kind of material. I will show you now. Okay, we'll be measuring shape parameter and corrected anisotropy, denoted capital T and P prima. Okay, these are two geometrical parameters, two geometrical statistical parameters from homogenized volume that is usually used in geology to characterize rocks that contain crystals or minerals with a given orientations. So we consider that this is of relevance in this kind of material because it will determine, or at least partially, the mechanical properties and anisotropy of this material. Okay, here I show an example of real images in the top and synthetic or generated images in the bottom. You see that the quality is not like exactly the same. The real images are a bit more smooth, and in the synthetic images you see some patterns, like it's like the kernel characteristics are just copied sequentially. That's not very important because what we want is to define the characteristics of the different phases. So if within the solid itself there are some patterns like that, it changes nothing because when we segment this, that's all the same material. So that's not really important. What we really want is, like you see these bridges, these white bridges, if they are orientated in a particular direction and have a particular size distribution, we want that to be reproduced by the synthetic images, because that's what will give anisotropy to the mechanical properties in this material. Oh, I forgot to mention the grains are silica grains or calcite, and I don't remember now. I think it's calcite. And this is saturated with a saline solution. The reason why it's saline is because some potassium salt was added to the water that allows X-rays to see this water. Otherwise, water will have a very similar absorption of X-rays than the rock material. So what you see in white is the water, and what you see in black is the ice. Because when you freeze salty water, the ice displaces the salt outside the ice. So the ice has less concentration of salt than the water. And the remaining liquid water gets a higher and higher concentration of salt. That's why we have higher and higher X-ray absorption in the remaining water, the one that is not frozen. So that's what we see in white in the images. Okay, so let's continue. So what we do is we propose parametric study. Where is it? Okay, here. In this table, we propose 3 different byte sizes and 1, 2, 3, 4, 5 different latent dimensions. So this makes 15 different cases, and we run the learning process for these 15 hyperparametric cases. 3 of them did not succeed because of memory, too much memory demand from the simulation. And the simulations that reached an end, there are some that you see like this, and this that do not reproduce any kind of successful image. So there are some like this, and these 3 that more or less look like our material. But now it's time to determine which of those, according to Jelinek plot, which takes into account anisotropy and shape functions, are more similar to the real images. So after some probability and statistics, we determine that the simulations 4 and 8 are the 2 that are more similar, statistically speaking, according to the geometric parameters, to the real images. So that's the 2 cases that we retain. I think 1, 2, 3, 4. It's this one, 4, 5, 6, 7, 8, and this one. So it's the case with byte size 8 and latent dimension 80, and byte size 16 and latent dimension 40. So these 2 are retained as a candidates for an optimal hyperparameter setting. And next, what we do is the same we saw in the previous paper. This is a workflow to determine mechanical properties of the synthetic images. So we do this for both the real images and synthetic images that we generate with the 2 cases that we retain in the previous step. So we get the X-ray CT image A, we mesh it. I jump one step, which is segmenting. I showed this before here. Here are the steps for segmenting using Euclidean distance transform, but now this doesn't matter. So we mesh it, we run a finite element model to determine the homogenized elastic coefficients of this medium. And we run this in the 6 degrees of freedom that we have in 3D to get all the coefficients of the elasticity matrix in 3D. Okay, there are 36 coefficients, but because of symmetries, there are only 1, 2, 3, 4, 5, 6, 7, 8, 9 coefficients that matter to us because there is symmetry between here and here. And according to this box plot, and because we run more or less 30 simulations for each case, so we can run tests that assume normality. We can compare these central tendence statistics with the real images, and we determine that the homogenized elastic coefficient of simulation 4 with a deviation of 7% is the best among all the simulations that we perform. Okay, so that's not good enough, maybe, for some scientific applications. This is 7% off the real mechanical properties. But as I said, the main purpose of this research was to determine the hyperparameters of the generative adversarial model. So now the next step would be to add to this diagram a supervision module using the hyperparameters that we already determined. So just very quickly, if you didn't watch my previous videos, a supervision module is something like this that, in parallel to the machine learning process, is telling the generator if the images are good or not in terms of physical properties. In this case, mechanical properties that are computed using FEM simulations. Okay, so that was all for this video. In the future, maybe I will present some generative adversarial network applied to medical images. So this will be images of brains that suffer an infarct or some other pathology like aneurysm or even an hemorrhage. I hope you like it. See you in the next video. Bye.